Good evening, everyone. So, in this session, we'll be beginning with the new chapter, right, of class 12 physics. That will be the ray optics and wave optics. In general, we call it as optics, right? So, we will be studying about the geometrical part of this optics, and then we'll be studying the wave nature of this light, right? That's the wave optics, right? So in optics in general, we study the properties and interaction of light with matter, right? And we know that light is the part of electromagnetic waves, right? Which gives sensation to our eyes, right? Or we can say that we're able to see everything around us because of the light, right? So actually, light itself is an electromagnetic wave, right? Talking about the wave nature, right? It's an electromagnetic wave, right? So it has the electromagnetic nature, right? It has its electric field component, it has its magnetic field component, right? So and important point about this light is that it does not need material medium for its propagation, right? Without material medium, it can propagate in vacuum, it can propagate in any medium, right? With different speeds, right? So the part of the electromagnetic radiation, right? Or we can say the part of the electromagnetic spectrum that we are able to see with our naked eyes, that part of the electromagnetic spectrum we call as visible region, right? There are different regions of the electromagnetic spectrum, right? There are gamma rays, there are UV rays, that's ultraviolet rays, there are X-rays, right? There is visible region, right? And visible region is that part of electromagnetic radiation which gives sensation to our eyes, right? So that we can see everything around us, right? Then we have IR region, that's the infrared region, right? We have the microwaves, right? We have the radio waves, right? So these are all the part of the electromagnetic spectrum. And from this electromagnetic spectrum, in this chapter, we'll be dealing with the visible region only, right? It's that part of electromagnetic spectrum which gives sensation to our eyes, or because of this region, we're able to see everything around us, right? And we know that in this visible region, there are actually seven different wavelengths, right? Seven different wavelengths, or we can say seven different colors, right? That we call as wave cure, right? That we call as wave cure. So wave cure in this visible region, we have the wave cure. It means seven different wavelengths, right? In the visible region, where V stands for violet, indigo, blue, green, yellow, orange, and red, right? So this is the part of the visible region of electromagnetic spectrum, right? So this was the basic introduction of light, right? Now talking about the different properties of the light. The speed of light, the first property is the speed of light, right? The speed of light is 3 into 10 to the power 8 meter per seconds, right? Approximately. And this speed is in vacuum, right? This speed is in vacuum. So the speed of light in vacuum is 3 into 10 to the power 8 meter per second, right? It's a very huge speed, right? And we also studied the electromagnetic radiation, right? Light is also electromagnetic radiation, where we studied that electromagnetic radiations carry the energy and momentum, right? So light also carries energy and momentum, right? So any part of the electromagnetic spectrum will actually carry the energy and momentum, right? So according to the Maxwell's proposed theory, the light is electromagnetic waves. It consists of electric field, varying electric field and varying magnetic field, right? And the nature of this electromagnetic wave is transverse, right? That means that the electric field vector and the magnetic field vector will be perpendicular to each other and also perpendicular to the propagation of the light, right? And the frequency or the speed of light in any medium, right, that will be given by the frequency of light multiplied by the wavelength lambda, right? Where lambda is nothing, it's the wavelength, right? Lambda is nothing, it's the wavelength of light, right? So these are the different properties of light. The first properties is that uh, the speed of light is 3 into 10 to the power 8 meter per second in vacuum, right? And it carries energy and momentum, right? It consists of varying electric field and magnetic field. That's the wave nature of this light, right? So, and similarly, we have the transverse nature of light, and the speed or velocity of light in any medium is given by the frequency times the wavelength, right? Where lambda is the wavelength of light in a particular medium, right? Now, these were the properties of light, right? So there's a term what we call as rectilinear propagation, right? So rectilinear propagation is actually describes the tendency of light or the tendency of electromagnetic waves to travel in a straight line path in a homogeneous medium, right? In a homogeneous medium. By homogeneous medium we mean to say that every if we let's suppose if we have this medium, right? This is the medium, right? This is the medium, then every direction here in this medium will be symmetric in nature, right? Every direction in this medium will be symmetric in nature, right? It means that whatever this light ray will face along this direction, the same will be faced by this light ray along this direction in this medium, right? So it means such mediums we call as homogeneous medium, right? So in homogeneous medium, light has the tendency, or electromagnetic waves have tendency to travel in a straight line path, right? So that tendency of light traveling in straight line path, we call it as rectilinear propagation, right? Rectilinear propagation. Then comes the definition ray. What do we mean by ray, right? So a ray of light is the line, is the path along which, or the straight line path along which the transfer of light energy takes place, right? Or we can say it's the trajectory, straight line trajectory along which the light uh, travels, right? Light travels. So that path we call as ray, and any ray can be represented by this, right? This is the representation of ray. It's a straight line, right? It's a straight line with the arrowhead. Now, a straight line actually depicts the path of this light, and arrowhead tells the direction of this light. So this is the ray of light. So ray of light is actually the path along which light travels, or light carries energy, or transfer of energy takes place, right? So the arrow represents the direction of propagation of light. So this was about the ray, right? Now there can be different types of rays, right? One type of ray we call as convergent ray, right? Or convergent beam. The beam is actually the bundle of rays, right? Beam we call it as bundle of rays. Beam is nothing. Beam of light. It's nothing. It's the bundle of rays. Beam is nothing. It's a bundle of rays traveling in a straight line path, right, or rectilinear path. Such bundle of rays, or such bundle of rays, we call it as beam. Now there can be different types of rays, or we can say different types of beams. One we call as convergent beam, another is divergent beam, and we have the parallel beam of light. So convergent beam is actually the set of, or we can say the beam of beam of ray of lights, which converge to a common point, right? Which converge to a common point. You can see here there are three rays, right? They form the bundle of rays, and you can see here they are convergent in nature, right? Because when these ray of lights are extended in the forward direction, they will meet at a common point, right? Or we can say they will converge at a common point, right? Such type of ray of light we call as, or the beam of light we call as convergent beam, right? Or we can say the diameter of the beam actually decreases in the direction of ray. You can see here the diameter of beam here is, this is the diameter of beam here, right? And this is the diameter of beam here. You can see clearly the diameter of the beam along the direction of ray of light actually decreases, right? Then we have the divergent beam, right, in which there is a common source of light, right? There is a common point from which the rays of light, or beam of light, emerges, right? And the diameter of beam actually increases along the direction of along the direction of ray of light. So you can see here the diameter of this beam continuously increases, right? And they emerge from a common source of point, right? Or common point. That common point we call such type of beam of rays we call as divergent beams, or we can say they diverge from the point of source, right? Then we have parallel beam of lights, in which the each and every ray of light are parallel to each other, right? Such ray of lights actually do not converge at all. They do not diverge, right? So they are parallel to each other, and the direction of parallel beam of light is fixed, right? And the diameter of parallel beam of lights remains same at each and every point, right? At each and every point, the diameter of the ray of light actually remains same or constant, right? So these are three types of rays. One is the divergent, another is the convergent, and the third one is parallel beam, right? Now, broadly speaking, about the optics, there are two branches of the optics. One we call as the ray optics or the geometrical optics, and another we call it as wave optics, right? So ray optics is nothing. It's the study of ray of light or the rectilinear propagation of light, right? It's the study of rectilinear propagation of light, or the light travels in the form of ray. While in wave optics, the behavior of the light is like the wave, right? That we studied in the EM waves also. So in wave optics, the light behaves like electromagnetic wave, right? So under many circumstances, we can say that the wavelength of light is actually negligible or very small as compared to the dimensions of the object or device, right? As in the case of ordinary mirrors and lens, right? So the dimension of the wavelength of light is actually very negligible as compared to the dimension of object with which the light actually interacts, right? So in that case, light behaves like a light travels in a rectilinear path, or we can say uh, the ray of light or the uh, light is actually governed by the simple geometric rules, right? Or we can say it follows geometrical optics in that case, where the object and the ray, the dimension of the object is much greater than the wavelength of the light, right? And the part of optics that deals with such phenomena is called as geometrical optics, right? So in wave optics, when the object is having the wavelength comparable, right, very comparable to the or greater than the object, right, to which it interacts, right? In that case, the behavior of the light changes, and we study that behavior of light under the heading wave optics, right? Now let's talk about the reflection of light, right? Now let's talk about the reflection of light. Now, a reflection of light is nothing. It's the striking back or the bouncing back of light, right? When instant ray of light strikes a given object, right? It's the bouncing back of light upon the interaction with the interface or the medium, and the light gets bounced back into the same medium, right? Such phenomena we call as the reflection, right? So it's actually the when light rays strike the boundary of two media, right? For example, we have here air and glass. A part of light is actually turned back into the same medium, and that turning back of the light into the same medium we call as reflection, right? So this ray we call as incident ray, right? And this ray we call as reflected ray. So bouncing back of light or striking back of the light into the same medium, right, upon interacting uh, with the two mediums at the boundary or the interface, right? Such a phenomena we call as reflection, right? So whenever the light interacts at the boundary between the two medias, right, there are two phenomena taking place at the same time. One is the reflection, another is the transmission, right, or refraction, right? So you can see here there are two mediums, medium one and medium two. Here, the light, some part of the light gets reflected back, and some part of the light gets transmitted or reflected, right? So at the two mediums, at the surface of the two mediums, both things are possible. Refraction as well as reflection is possible, right? Here you can see also there's a rigid surface, right? Rigid irregular surface. So instant ray of light strikes the surface, and this ray of light, instant ray of light, bounces back from the surface, right? And is reflected back into the same medium. So once again, this is the reflection, right? So reflection of light is simply the bouncing back of light upon moving from one medium to the another medium at the interface. This is what we call as reflection. Now, reflection of light is governed by certain laws, right? It follows certain laws, right? So reflection follows certain laws, and those laws we call as laws of reflection, right? Those laws we call as laws of reflection. So let's study these laws one by one, right? These laws one by one. The first law of reflection is that the incident ray. So this is the incident ray, right? This is the surface, right? Or we can call it as mirror or the surface. This is the incident ray. This is the surface, right? and this is the reflected ray, and the normal or perpendicular to the surface at the point of striking this surface, right? Let's call this point O. Now this incident ray strikes the surface at point O and gets reflected back into the same medium, right? Now there are three things. One is the incident ray, another is the reflected ray, and the third one is the normal, right? Normal is the perpendicular at the point of incidence, right? At the point of incidence. Now, first law of reflection says that the incident ray, incident ray, right, comma reflected ray, and normal all lie in the same plane, right? All lie in the same plane. So the first law says that incident ray, normal, and the reflected ray all lie in the same plane. You can see here. Let's suppose incident ray lies in XY plane, then normal must lie in the XY plane. Then the reflected ray also must lie in the XY plane, right? So their plane must be same, right? Their plane must be same, right? They must lie in the same plane. So the reflection takes place in such a way so that all the three objects, that's the incident ray, normal, and the reflected ray, lie in the same plane, right? This is the first law of reflection, right? Now, second law of reflection says that second law of reflection the second law of reflection says that you can see here, this is the angle made by the incident ray, right? This is the angle made by the incident ray. This is the angle made by the incident ray with the normal, right? And this is the angle made by the reflected ray with the normal, right? So second law says that the angle of incidence, right? So angle of incidence is nothing. It's the angle made by the incident ray with the normal. That's angle of incidence, and the angle made by the reflected ray with the normal. That's angle of reflection. Second law says that angle of incidence must be equal to angle of reflection, right? So this is nothing. This is the second law reflection. So reflection takes place in such a way, both all the three normal, incident ray, reflected ray lie in the same plane, and angle of incidence is always equal to the angle of reflection. So these are the two laws of reflection, right? Now let's talk about the different definitions and different concepts of the ray optics. The primary concept to understand the ray optics is the understanding of the object, right? So object is nothing, it's any source of light, right? So light rays incident on an optical element is responsible to define object, right? So object is defined actually as the point of intersection of incident rays. Light object is nothing, it's the source of light, or it's the point of intersection of incident ray of light. So it's the important point here. Actually, the object is actually the intersection of incident rays, right? So object is the point where actually the incident ray intersect each other, right? So incident rays can be of two types, right? One is the converging, right? You can see here the incident rays can be of two types. One is the converging, another is the diverging, right? Now you can see here, this is the converging incident ray on this optical element. Let's suppose this optical element is a plane mirror here, right? It's a plane mirror here. Let's suppose this optical object is plane mirror here, right? Now you can see it's actually converging, right? It's converging. These incident rays of light are converging. So these incident rays of light will intersect at each other at this point virtually, right? Because you can see here, there is an optical element or the plane mirror, because when the incident ray of light strikes this mirror, it will reflect back right in this direction, and this ray of light will also reflect back in this direction, right? So they do not actually meet at this point, right? So this point is a virtual point, right? So incident rays of light appear to be meet or intersect at this point O, and this point O we'll call it as object, but they are not actually intersecting at this point, right? So this object is called as virtual object, right? This is nothing, this is virtual object. This is the virtual object. Or we can say the converging incident rays of light form the virtual object. Similarly, for the diverging rays, so this is the diverging ray, right? Now here actually the incident rays of light actually intersect at this point O. So this object will be called as a real object, right? This is nothing, this is the real object. So real object is formed when incident rays of light are diverging, and the virtual object is formed when the incident rays of light are converging in nature, right? So we have two types of object. One is the real object and another is the virtual object. For virtual object, we have converging rays, and for the real object, we have diverging rays. Now let's discuss what do we mean by actually the image, right? In physics, right? So image is actually defined as the point of intersection of reflected or refracted rays. It means that when the incident rays of light incident rays of light or we can say interact with the optical element, right? Once the incident rays of light interact with the optical element, right, the interaction can be reflection, the interaction can be transmission or the refraction, right? Then after interacting with the optical element, the point of intersection of the reflected or the refracted or we can say transmitted rays is actually the point of formation of the image, or we can say that point is called as image. Or we can say image is nothing, it's the point of intersection of reflected or refracted rays, right? So you can see here, we have placed in front of a plane mirror, right? In front of a plane mirror, we have placed an object, right, at a distance of t, right, at a distance of d. At a distance of t, we have placed a plane mirror at a distance of t. Now, these instant rays of light strikes this mirror, right? Let's suppose they will strike this mirror at an angle of incidence, at some angle of incidence I, right? Angle of incidence I. Then this angle of incidence has to be equal to the angle of refraction, right? This has to be equal to the angle of refraction, right? So similarly here, they will strike, they will move in such a way such that angle of incidence will be always equal to angle of refraction, right? So point O is the object, right? Now these are the reflected rays, right? These are nothing, these are the reflected rays upon the interaction with the optical element. These are the reflected rays. So once the incident rays of light interact with this optical element, right, or plane mirror, these ray of lights are reflected, right? These rays of light are reflected. And when we extend these reflected rays in the backward direction, they virtually meet at this point, right? So this point of intersection is nothing. This point of intersection we call as image, right? And they do not actually meet at this point. They meet when we extend the reflected rays in the backward direction. So we can say the image formed here is virtual image, right? It's a virtual image, right? Virtual image. The image formed here is virtual image. So object can be virtual, object can be real, image can be virtual, and image can be real as well, right? So in case of plane mirrors, the point one is in case of plane mirrors, image formed is virtual for diverging rays. For diverging rays. So for diverging rays, the image formed is virtual, right? And you can see the object is at the same distance from the mirror as the image is from the mirror, right? Or we can say that the distance, now you can see the distance of image from the center of this mirror is d, and the distance of object from the center of mirror is also d. Or we can say that object distance in case of plane mirror, object distance is always equal to image distance, right? Image distance, image distance, right? And the third point is in case of plane mirror, there is a lateral inversion, right? There is a lateral inversion of image, right? What does it mean? It means that the left of the object appears as right in case of image, and the right of the object appears as left in case of object, right? So in case of image, the left of object appears as the right of image and the right of object appears as left of image, right? So this is what we call as lateral inversion, right? Lateral inversion. This is what we call as lateral inversion, right? Now let's talk about the angle of deviation, right? Now you can see here, uh, this is the plane mirror, right? This is nothing, this is the plane mirror here. This is the incident ray of light, this is the reflected ray of light, and this is the normal here, right? This is the normal. This is the normal end, right? This is the angle of incidence, right? This is the angle of reflection, R, and angle I has to be equal to angle R, right? Angle I has to be equal to angle R, right? Now, calculating the angle of deviation. So, angle of deviation is the angle deviated, that reflected ray deviates from its original path, right? The angle by which the reflected ray deviates from its original path, that angle we call as angle of deviation, right? You can see here, the originally the incident ray of light was along this direction, right? It was along this direction. This is the original direction of incident ray of light, right? Now this is the direction of the reflected ray. But this is the angle through which the incident ray is actually deviated from its original path. So this angle we will call as angle of deviation, right? Angle of deviation. The total angle on the line is equal to pi or 180 degree, right? And this pi will be equal to angle of incidence is equal to angle of reflection, right? We can write it as I plus I, right? I plus I, right? I plus I, and then there will be this angle what we call as angle this angle is called as delta, right? Plus delta, right? Plus delta. So therefore, delta will be nothing. Delta will be nothing. It will be pi minus 2 times I, right? It will be pi minus 2 times I, or we can write it as angle of deviation is always equal to 180 degree minus 2 times angle of incidence, right? So this angle we call as angle of deviation or deviation of ray of light from the incident ray of light. So this angle we call as angle of deviation. So angle of deviation is nothing, is the deviation of, it's the deviation of incident ray incident ray from actual path upon reflection, from actual path upon reflection, right? So upon reflection, this is the deviation, right? This is represented by delta, right? So this is the angle of deviation, right? Now let's try to solve this question. The question is that find out angle of deviation, right? You can see here the incident ray of light is incidented at an angle of incidence 30 degree, right? Angle I here is equal to 30 degree, right? So angle R has to be 30 once again, right? This angle will be once again 30 degree, right? This angle is R. So angle I has to be equal to angle R, right? That has to be equal to 30 degree, right? Because of the laws of reflection, right? Angle of incidence must be equal to angle of reflection, right? Now the total angle we are here on this line will be 180 degree, right? Or we can write delta as that is 180 degree minus 2 times the angle of incidence, right? 2 times the angle of incidence. So the delta will be here 180 minus 2 times 30, right? It will be 180 minus 60, right? That's equal to 120 degree, right? That's equal to 120 degree. So angle of deviation here is nothing. That's equal to, so this is the angle of deviation, right? Delta, that's equal to 120 degree. The angle of deviation for this ray of light will be 120 degree will be the deviation, right? Now let's talk about the reflection, right, from spherical surfaces, right? Now there are different types of spherical surfaces, right? You must have heard about the concave mirror, right? Concave mirror and convex mirror as well, right? Now let's talk these mirrors in detail, right? What are actually the spherical mirrors? Spherical mirrors are nothing. These are the mirrors which has been cut out from the sphere, right? From the sphere. Let's suppose we have a complete sphere made of complete mirror made of sphere, right? Complete mirror spherical in nature, right? We have complete mirror spherical in nature, right? If this is the mirror spherical in nature, right? Of radius r, right? Of radius r. If we have this mirror which is spherical in nature, right? Of radius r. Now from this mirror, what we do is that we just cut out the portion of this mirror, right? If we cut the portion of mirror from this point and this point, what we will be left with, that will be this part only, right? That will be this part only, right? This part is also a mirror, right? This part is also a mirror. Now the radius of this mirror, since this part of the mirror was the part of this sphere, right? Now the radius of this mirror will be also the radius of this sphere, right? Or we can say spherical mirror uh, is part of hollow sphere, right? Of which this mirror was a part, right? Or we can say spherical mirror is nothing. It's a mirror piece cut out of a spherical surface, right? Or we can say this mirror is having the same radius as the radius was there for this original sphere. That's the radius r, right? That's the radius r, right? Or we can say spherical mirrors is the part of sphere, right? Part of sphere from which it has been cut out, right? Now, there are different types of spherical mirrors. One spherical mirror we call as concave mirror, another we call as convex mirror, right? Now, depending upon the polishing of the surface, right, how the polishing is done for formation of these mirrors, there are two types of mirror, right? Here, first type is the concave mirror in which the outer surface is polished, right? Outer surface is polished and the inner surface is reflecting surface, right? So this is the concave mirror, right? This is the concave mirror. This is called as concave mirror, right? This is nothing. This is the concave mirror. And here the inner surface is actually polished, right? Inner surface is polished and the outer surface is reflecting. So this mirror we call as convex mirror, right? Convex mirror. And both these mirrors are part of a spherical surface or spherical mirror, right? So we can say concave mirror and convex mirror are the part of the sphere, right? Or we can say the concave mirror will have the radius, same radius as that of sphere from which it has been cut out, right? So there are two types of mirrors. One is the concave and another is the convex mirror, right? Now you can see here we have the concave mirror here, right? There are certain, you can see here now this concave mirror is the part of this sphere, right? It's the part of this sphere. And the radius of this sphere is r. The radius of this concave mirror will also be equal to r. And this radius we call as the radius of curvature, right? This radius we call as the radius of curvature. So let's define each and every term one by one for this mirror. One is the pole, right? One is the pole. So pole is nothing. It's the central part of the mirror, right? It's the central part of the mirror, right? So this point is what we call as the pole of the spherical mirror or pole of this concave mirror. This is nothing. This is the pole. The center of the mirror or the center of the aperture of a mirror, right? Aperture is the part of the mirror from which the reflection or the refraction takes place, that we call as the aperture, right? The center of this aperture we call as pole, right? Then we have principal section, right? uh, you can see here m to m dash, that's what we call as principal section. Actually this is the part of the mirror from which actually the reflection will take place, right? So m dash will be m dash will be the principal section, right? We call it as principal section, right? Now the third point is the center of curvature. So center of curvature is nothing, is the center of that sphere of which the mirror was part, right? Then this spherical mirror or this concave mirror was the part of this sphere. Now the center of this sphere will be called as center of curvature, and this center will be the center of curvature for this concave mirror as well, right? Then we have radius of curvature. So radius of curvature is nothing, it is the radius of that sphere, right? Of which this mirror was a part, or we can say from which this mirror was actually cut out, right? Then we have the principal axis. The principal axis is the axis passing through the center of curvature and the pole of mirror, right? So here CP is the principal axis, right? CP line is the principal axis, or we can say it's the line passing through the center of curvature, right? And the pole of a mirror, right? So this is what we call as the principal axis. So there are four terms basically: center of curvature, radius of curvature, principal axis, and the pole of a mirror, right? So these four definitions are very important to understand the concept of the spherical mirrors, right? So same goes with the convex mirror also, right? The convex mirror also has the center of curvature, pole, and radius of curvature, right? So in the tomorrow's lecture, we'll be discussing, right? Day after tomorrow, we'll be discussing about the different image formation in case of spherical mirrors and the particularly about the concave mirror and the convex mirror, right? We'll be discussing the image formation. We'll be discussing the what we call as mirror formula, right? For this concave mirror, right? And we'll be discussing different questions related to it, right? So that's it for today for this session, right? We'll meet day after tomorrow, right? Till then, take care and goodbye.